So what we're going to go over in Chapter 2, we're going to talk a little bit about networks again. We've already kind of talked about the flow between networks. We're going to expand on that a little bit. And then we're going to talk about switching concepts. We've already talked about our broadcast and our collision domains and the different ways that those are separated and what kind of devices separate those. So this is just an illustration. When we had our old legacy networks with our hubs on it that repeated everything back out, there's a single collision domain. Only one person can talk at a time, so obviously that's not ideal. So again, what happens in a collision? Two people try to talk at the same time. The packets collide. Nobody hears anything because the data gets lost. Obviously we don't want that. So this kind of network is laggy. Only one person can talk at a time. It's slow. It's inefficient. So let's look at the way in a modern network again that we're going to break that up. So this is our typical network design that we still use today. So this becomes a little bit better. So we still have one broadcast domain by default. Why do we have one broadcast domain? There's no router. The router's the thing that breaks that up. We don't have that in this illustration. So we have one broadcast domain. And each connection on a switch creates a separate collision domain. So over here, you know, we've just got two boring workstations connected to a switch. Over here it gets a little bit more interesting. So we have a workstation connected to the switch, and then we have a wireless access point. So what does that access point do?
Allow remote access?
No. Roger, come on.
Extends the signal.
Yes, it extends the network, which you already a step ahead of me because that was my next question. Somebody read the chapter, right? So this propagates a wireless signal and it extends the range of the network. Before we had this wireless access point, if it was plugged in, it worked. Well, now you add this access point and you're allowing wireless access to this network as well. So it gives us a little something extra to think about. So this extends our network. So now, what happens to all the people that are connected to this? They're on one collision domain because the access point's plugged into the switch. Every port on a switch is a separate collision domain. All these people are now in one collision domain. So that could cause some problems, especially when you think about it on our campus network. If we just had one really big, really strong access point in the middle of the school and that's it. We have tons all along the hallway and everything that you can connect to at different points, but if we were all on one, we'd never get anything done. Because packets would be colliding, we'd be using up all our bandwidth, and nothing would ever get accomplished. So now we have to deal with our wireless nodes. We have to think about those. Now there's more traffic on our network because you don't have to be plugged in to use it. You can be wireless. And also, there's two different kinds of traffic to deal with. So now, when we think security-wise, we have to think about wired and wireless, and they're different. There's a lot of different things that are going to come into play with those two. So we talked about how a router creates broadcast domain boundaries. Every port that's in a router is its own broadcast domain, right? So now we have two broadcast domains, and how many collision domains? 10, right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because every port in a switch is a separate collision domain, and that includes the port that's going out to the router or some other device. So now, we just increased our broadcast domain, so we would have less traffic, right? But we also just created more collision domains. So what are we going to do to circumvent that? So now you can add devices and you can make things separate a little bit, but you kind of just change the problem essentially. Well, the way that we do that on a modern network is a VLAN. So a VLAN is a virtual LAN. So our layer 3 switches, our managed switches that we talked about, have the capability to console into them and make changes to the port configuration. So what you're looking at here is an example of this. So I may have one physical, I'm sure this is a 48 port switch. Yeah. So I have a 48 port switch here. And I have different departments that my business is segregated into. I've got sales, I've got marketing, I've got engineering, I've got production. I've got different segmentation throughout my business, and I want to reflect that in my network as well. So what I'm going to do is I'm going to go into, say, okay, I've got 3 salespeople, they've got 3 wired PCs. I'm going to go into the configuration of the switch, and let's say this is port, 7, 8, and 9. I'm going to say, here's a VLAN that consists of 3 ports, 7, 8, and 9. Then I'm going to do the same for engineering. Okay, they're 10, 11, and 12. So I'm going to go in, and even though they're all physically connected to one port, I'm going to logically separate them. And when I logically separate them, I'm saying people on the sales VLAN, the sales virtual LAN, can't talk to people on the engineering virtual LAN. They're separate. Why would I want to do that? Reducing traffic, absolutely. From a security standpoint, if somebody on the sales VLAN gets like a really bad virus, I don't want it to spread to all the other stuff that it could possibly be connected to. So I'm basically segregating this stuff for the purposes of being able to keep a better hold of the traffic. The broadcasting and stuff like that goes way down, right? And so this is what a VLAN is. Now, one thing I want you to notice is that we have a router here. The router's connected to the internet, so you know that's not a big deal. But if you want to go between these different VLANs, you have to have a router. So it's treating it like it's a completely separate network, because it is. Even though you may have all these things plugged into the same switch, logically they're in completely different places. So you would have to have a router to go in between all these different VLANs. Here's an example. Here's another switch down here. So this might be located on the other side of the building or something. So we have other VLANs that go with our sales and with our engineering. So even though these are connected to different switches, we have something in between here, a trunk, we'll talk about later, that's going to be able to connect these two that says, okay, these salespeople in VID2 and these salespeople in VID2, they can talk to each other. But if you want to go from VLAN, the sales VLAN to the production VLAN, well, you can't. They're on different networks. So that's an example of how, instead of buying all these devices, these different switches and these different routers and trying to interconnect everything, and then having all these points of failure where, well, if this switch breaks, all these people can't use the internet, you know, that kind of stuff, we might just configure something. And layer 3 switches are not that expensive, maybe 150 bucks. You could just configure it to fool it, kind of, to make it think that it's logically separated. So talking about transmitting data, we've talked about collisions. So let's talk about what the network does when it sees a collision, because it already has something in place for that. So this is a principle of Ethernet technology. This is one of the things about Ethernet that makes it work. So CSMA-CD stands for Carrier Sense Multiple Access with Collision Detection. That's a lot of words, but once you see what it means, it'll make a lot more sense. So, when you look at the graphic that we have here, so the host is sending out a signal. While it's sending that out, it's going to monitor the line to make sure that no one else is trying to transmit anything. So that's what you're seeing in the first little section here in this picture. If it detects something gets sent out, as you see in the second part, a jam signal is sent. So it causes everybody to stop sending everything out. Like when you pick up the telephone, if you remember this, and you got a busy signal, that kind of thing. You know something else is happening, So nothing can happen on your end. That's your jam signal. Then the other computer is going to wait a random number of seconds and then try to send again. If it sees the jam signal out there still, the whole thing will happen again, and after 15 times it'll time out and say, well, I guess we can't send anything right now, the network is busy. So this listening on the line, so to speak, and waiting to see if that jam signal's gone, that's what CSMACD is. So when you think about it, carrier sense, the carrier is the medium, is the wire. And it's sensing, trying to see if there's something else being used on the medium. So our multiple access is our multiple people trying to access this medium to move data. And then the collision detection is detecting the collision, literally, and then doing something about it. So when you break that acronym down, it kind of starts to make sense. With wireless, we have the same thing, but we call it collision avoidance, which we'll talk about later on. So this is a principle of Ethernet that makes sure everybody can talk when they're on the same collision domain. We want to break those collision domains down to as small as we can so that we don't have to wait on things, to wait on a jam signal and a timer to happen, but this is what we do when that does happen. Any questions about that? Another thing that you're going to talk about all the time is half duplex versus full duplex. So here's an example of a collision on a hub. So in this case, this computer is trying to send a message. And we know when this computer sends that message, it's going to get repeated out these 3 wires, because that's what hub does. Well, both of these people are trying to do this at the same time, and that makes a collision happen. So in a half duplex scenario, a half duplex is like a hub. It can either send, it can receive, but it can't do both at the same time. That's what half duplex is. It's like a walkie-talkie. So you can push the button and you can talk, or you can depress the button and listen, but you can't do both at the same time. That's what half duplex is. Full duplex is being able to send and receive at the same time. So here's an example. We've got a switch and a hub. A hub operates in half duplex. A switch operates in full duplex because it can do both at the same time because it's smarter. It's not just repeating things out, it's a smarter device. So we've got collisions occurring on this hub just like we did in the previous picture. But this switch over here is so smart, the hub, the port that's connected to the hub has been configured to say, okay, we expect half duplex transmissions out of this wire because it's connected to a hub and that's all the hub knows to do. So that's an example of full versus half duplex in action. On the switch, all 4 people that are connected can transmit simultaneously because the switch is smart enough to be able to pick up that stuff and arrange it in the way it's supposed to go to the people that it's supposed to go to. So what's important to note here is the switch has the port on it that's been configured. Not saying it came out of the box that way, but it's probably a layer 3 switch and it's been configured so that that one port that's connected to that hub is half duplex for that reason. So you might say to yourself, how would you go about changing those configurations? So here's an example. If I go to, this is a screenshot from my instructor PC. This is in like computer management, device management. You can go and look at the NIC driver and then look at configuration. So here you can see that I have the option, even though I have a very new NIC, I have the option of making it full or half duplex. I could throttle my speed down if for whatever reason I had a program or something that needed to do that. If it couldn't accept 100 megs, in this case it's just set to auto because it's smart enough to know. But you can see I've got stuff here, VLAN, VLAN ID. So that is how you would go about seeing what your configurations are. Making configurations to the VLAN you would have to do on the device, on the switch. We've talked a little bit about MAC addresses and what they look like. We know they're hexadecimal, right? We know that they are 48 bits of information. We know that the first half of that is the organizationally unique identifier, and that is coming from the vendor, the one that manufactured the NIC. So all of Dell's numbers look the same. All of Light-On's numbers look the same. And we saw in Wireshark, and we saw Dell, and then you would see unique numbers from the source. That's indicating that NIC was a Dell NIC. And here's the part that you actually care about, because that last bit is assigned by the vendor. So this denotes the vendor. This is assigned by the vendor to be the unique part of the address that nobody else will ever have, because they're all their own unique snowflake, right? So when you think about it, the vendor assigned bits, you might look at that and think, that's not a lot of numbers. I'm sure they make a lot of things that have NICs in them. And you would be right. But introduction to binary, so what are our choices with a binary number? I've got 2 digits it can be. What are they?
0 and 1.
0 and 1, right? That's it. So I start out with 2. And if I want to see how many possible combinations I would have in this vendor assigned section, it's 2 to the 24th. Okay? So 2 to the 24th is 16,777,216. So that tells me that within these last 24 bits of this address, I have almost 17 million different combinations that I can make before I start running into duplicates. So when you look at it that way, well, it kind of makes sense why everyone would need to have their own unique MAC address, right? So here's a little bit of, we're not going to go over every single thing in this at all, but this is kind of what a frame looks like. So remember we had the video of the guy a couple weeks ago with the different hats on, and he would hold this frame that had the different pieces. This is what he was kind of simulating. So he took a bunch of things off, but the destination and the source, they were a big deal, right? And they would change as they went. So a layer 2 destination looks like a MAC address. A layer 3 destination looks like an IP address, right? So as we saw that get encapsulated going up the layers, it changed a little bit. But the big part that I care about y'all knowing is the destination, the source. The type, we'll talk more about that next week, but the type is Ethernet 2. Once upon a time, there were all kinds of different Ethernet types, and it was really confusing, and that's why they created the OSI model, so everybody could talk to each other, not just brand-specific things. And then we've got the data. You've got 1,500 bytes of data in that part. And the frame check sequence, that's just the thing that determines if there's been an error in transmission, right? That's our error detection, not correction, right? Detects for an error. So this is what our frames kind of look like. So that's what you'll end up seeing. We'll talk more about that next week. But for now, I just want you to know that's kind of the stuff that's in it. Okay. Has anybody ever messed with decimal to binary conversion? Okay, good. So you might find this pretty easy. This is a really, really pivotal part when we get to subnetting in a few weeks. So if you go ahead and understand this now, you'll just be that much more ready to go when we get into subnetting. Okay, so a byte is 8 bits. So when we think about the places for any bit of information, any piece of information, let me put it that way, this is what it looks like. So our first place is a 1 value, and then you notice we kind of double as we go up. it always helps for me to remember it by starting at 128 and then halving all the way down. So if I want to convert a number from binary to decimal, I'm going to end up with something that looks like this. So if I want to convert this to decimal, what I care about is what place is turned on and what place is turned off. A 1 is on, a 0 is off, right? That's the only way computers talk. So if I'm starting down this first one, which I normally start at is 128. So 128, and then I halve down 64, 32, 60, yeah, 8, 4, 2, and 1. So if I want to convert this to decimal, so our binary is a base 2 system. There's only 2 options. Our decimal is a base what? 10. Because you got 0 too.
Yeah.
We always forget about 0. You won't forget about it anymore after you subnet, because that's all we talk about, right? Okay, so we've got going from a base 2 to a base 10. If I want to convert this, this is how I do it. I take all my things that have a 1 beside them and I add them up. That's it. So this has a 1 beside it, so 128. This doesn't, so I don't care about it. This is a 32. I'm going to add 32. 16. Not turned on, not turned on, not turned on, and 1. So when I add all of these things together, I get what the decimal equivalent is. That's it. So 10. Look, I don't Common Core. I add old school style. So 8 and 2 is 10, 16, 7, carry the 1, 3, 5, 6, 7, 177. Show off, Brian. So this number in decimal is 177. That becomes really, really, really super important in like 3 weeks. When we'll do conversions just all over the place. So these 8 bits equals 1 byte of information. So if I want to communicate 177 to a computer, I'm going to communicate that. That's all that means. Now, conversely, if I want to go backwards, $245. Let's do that. Okay. So I want to figure out if I want to go to binary. How would I do that? So let me set up my thing here. So here's my bit positions. So I want to figure out how many times 245 goes into that. So, how many times, no, I said that backwards.
That goes in there.
Yes, how many times this goes into that. That's what I want. So, how many times is 128 going to 245? 1. Basic, is this number smaller than this number? And if it is, you put a 1 there. Okay, so now I've got 245 I started with. And I've subtracted 128 from that number. I've represented 128 of that number by putting a 1 right there. So, quick draw. What's 245 minus 128? 117. He's fast with the numbers. Okay, 64 into 117 goes into it, right? Yep. Subtract 64. And I have I have 5 left, right? Is that right? If I mess up, y'all better tell me. Don't be shy. It's okay if I mess up now. I've done it like at least a couple times before, right? Okay, 32 into 45, 54. 1, 32. Now I'm down to 21, 16. Yep. Now I only have 5 left. 8? No. 8's bigger than 5, so that won't work. 0. 4 is not bigger than 5 though. So put in a 1. Now 5 minus 4, let me go over here a minute, is 1. 2 is bigger, so that won't work. 0. And then 1, I put another 1. Now I've used up everything I need to represent 245 by using binary. If I wanted to check that, 128 plus 64 plus 32 plus 16 plus 4 plus 1. And I should have 245. Right? Make sense? Yes, sir.
Why you skip the 3 out?
What 3?
Like, oh, no.
2.
Never mind, I'm choosing.
Oh, yeah.
Well, why you got the 1 on the 4 then?
Why do I have the 1 on 4? Okay, because I was here, and 4 goes into 5 one time,
Okay.
with a remainder of 1, which I represented there.
Okay.
Right? Okay. Alright, I'm going to go ahead and move on to the next thing. You'll have plenty of time after I get done to work on that, so don't worry. We've got one more conversion to worry about. We've talked about hexadecimal. So let's talk about what hexadecimal is. So hexadecimal is a base 15 system. So it uses 1 through F. So once we hit 9, we start using letters. So that's our difference between hexadecimal and decimal. So as you could probably guess, it's a little bit trickier than just 1s and 0s. So let's talk about what that is. So we've got the base 16 system. So we're going to divide everything by 16 and get our remainder, and then we're going to write the remainder in hexadecimal form. So that's what our difference is going to be. So let me give you an example of that. That includes a letter. Let's do 58. 58 in decimal to hexadecimal. So we can set it up like long division. Lord have mercy. It won't be that long, though. How many times does 16 go into 58? 3. So what's 3 times 16? 48?
This one. That's it.
Yep, okay. Which gives us a remainder of 10. What is 10 in hexadecimal? An A. So if you want to convert 58 in decimal to hexadecimal, it would end up being 3A. That's a little wacky. I know. We're definitely not used to thinking that way. There's going to be a couple problems on your homework that are hexadecimal related. We're not going to do much outside of that. When you get up to different classes and you're talking like your Cisco classes, you'll work more with that. So I just kind of want you to be familiar with it as far as what we just talked about there. So I have one handout for that. I'm going to go ahead and keep going with the presentation and let you all work on that when I get done. It's only one page this time. Okay, so let's talk about one of the funner parts of networking. Is anybody in here colorblind, by the way? Oh, good. Last semester I went through cabling and someone was colorblind and it was really difficult. It's like, how do I explain to you? I don't know what you can see. How do I explain to you? We got through it though. So the thing with cabling is you can configure all the Cisco stuff in the world, but if you can't make a cable, it's like, really? Cabling is one of the fundamental parts of networking, so that's why we're going to go over it. So you really need to understand there's 3 kinds of cables. There's just straight through, a crossover, and a rolled cable. So we're going to look at what that means, and we're going to talk about how our wiring standards work. So when you pull apart a wire, when you cut off the top of it and you kind of peel the cables out of it, you see 8 individual little cables, 4 different pairs, and they have a color to them. So that color is really significant. So just like we have standards with everything else, our OSI model, our Ethernet 2 frames, we have a standard as far as the color of the jacks that go on our Cat5 cables. That makes a really big difference. So the standard that you typically see used is called T568B. So a bunch of people got together at some big wig organization and decided this is what our standards are going to be for everything. The colors are not as easy to see here as if you're looking at them on your presentation on your computer. But this 568B, we refer to this as orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. To me, the brown and the orange are always kind of difficult to distinguish, but when you actually see it on a real cable, it'll make more sense. And we're going to do that in class Wednesday when you come in. So on another thing I want to mention, this little thing that you clip down and plug it in the wall and let go and it clips it in is called the boot. So when you're looking at this wiring, we refer to this as pin 1, or orange white as pin 1. And it's the first pin that's lined up right here. So when you're looking at putting the wires into a jack, you want that clip part to be down. And you want the flat part of the jack to be facing you. We'll go over that more on Wednesday. So here is what our wiring standard looks like. And I'm totally going to ask you a bunch of times what those colors are. I promise. And I'll make you put them in all different ways so that you remember it. So, our straight through Ethernet cable. So when you actually put a jack on, you use all of the wires that they've given you. But there's only 4 of these that actually get anything transmitted and received on them. So why do we put the other ones into it? Well, it's a standard, and if we didn't, it would get kind of messy. The wires might get dusty. It might cause something to go bad later on. So we put all the wires in. But on a straight through cable, here's what happens. So this is a computer connected to a what?
Switch.
Switch, right? So I would use a straight through cable if I was connecting a computer to a switch. The straight through is the standard, right? We have other weird ones. You see the straight through way more often than you see anything else. So data gets transmitted on pins 1 and 2 on both sides. So we've got our 1 and our 2, and you can see they're a slightly different color. And then data gets received on 3 and 6. That's how the full duplex works, right? Because both people have their own lines to transmit on, and both people have their own lines to receive on. So they can both talk. So we refer to this as a straight through cable. The wires go straight through to each side. So we would use this if we're connecting our host computer to a switch, like in this instance. If we're connecting a router to a switch, there's several different applications for each type of cable. So the first one that we want to go through is the straight through, because it's the standard. The thing, like if you've got a computer plugged in from your computer to the wall, it's a straight through. The ones that we commonly see when we're working with the end user PC. Now, another one that's kind of different is the crossover cable. So every pair can transmit simultaneously. So we would use this if we're connecting from switch to switch, or if we're connecting from PC to PC, and you want to transmit between 2 PCs, which is kind of weird. We don't do that very often. Now we use USB and things like that. But if we wanted to, this is how we would do it. So we would receive on pins 1 and 2, and then we would transmit on 3 and 6 on each side, right? So on this device, we flip things around a little bit so we can cross-talk, so to speak. That's not what it's called. But the talk can cross between the 2 computers. So now we're connecting in a little bit different way. So when you do that, your colors are going to look different on one side. So one of them is going to be your 568B, and the other one's going to be 568A coloring standards. We'll talk about those in just a second. Just know that you're switching things around, right? So if we wanted to know when we were supposed to use those, the straight through cable, we go from a router to a switch and from a workstation to a switch. So that kind of explains why we would see these way more often, because most of our things are going to be that kind of connection. Then our crossover cable, if we're going from a device to a device, like a switch to a switch, a router to a router, or if we're going from a router to an individual PC. So here's our crossover cable and what that looks like. When you add in all the other wires, everything is connected. The only change is that we have switched a couple of the colors. So going from a regular straight through cable to a crossover cable, we have two colors that change, the greens and the oranges. So if you can remember the acronym GO, it'll help you remember to swap the greens and the oranges. And that will help you to get a crossover cable. Our rolled Ethernet cable, this is the last kind, I promise. So this is, if you wanted to console into something for configuration purposes, if you wanted to use your workstation to console into a layer 3 switch or a router to configure something, you would need a rolled cable. That's kind of a special circumstance. You can also call in with like a console in with like a serial cable. The problem is, not a lot of stuff has serial connections on it anymore because it's kind of old. So we might use this instead. So you take the normal straight through wiring on one side, and then you just flip all the colors on the other side. So you're just reversing everything. And that's what a rolled Ethernet cable looks like. Really special. I'm not going to ask you to make one. Really weird. I just want you to know, take a normal one and flip it. So when do we use each cable? We've kind of talked about that. If this helps you at all, between a crossover and a straight through, if you can find some pattern, sometimes this chart helps people as far as which device and then which cable you would use if you're connecting to those devices, whichever helps you. So we've talked about consoling into things. The way that we would do that is that we would use an emulation program. PuTTY is the big one. And we'll talk way more about emulation next week and what that means. But essentially, you're kind of fooling your computer into being able to connect to it with certain configurations that you're going to put here. We will not do that in this class. I just want you to know that it exists right now. You can console into things, use your rolled Ethernet cable, and simulate a serial connection if you wanted to. The thing that you plug in to do this, you can console in with a little USB type cable, or you can do it with your rolled Ethernet cable in that spot. And it'll have a port listed on the back that says, this is the console port. And then you can use whichever one you want to. That console port is that mini USB. It's one of the things I hate about USB. It's super great, but doggone it, there's like 6 different ends. If you really want to nerd out, Office Depot sells like a little package that's got every possible USB end. I have one of those and it's changed my life. Trying to carry around all those different cables and fit them all in. No, just a little thing that you can take on and off. So, so we've talked about what we would use then. So here's a question. If we're going from switch to switch, what kind of cable would we use? The crossover. Alright, and if we're going from the router to the console computer, what would we use? Rolled. A rolled, exactly. Okay, so the last thing that I want to talk about today is encapsulation. Again, going back to the video of the guy with the frame, and he'd pass it up to the layer and they'd add something, pass it up to the next layer, they'd add something, and as they were going down, they were taking things back off of the layer. That's encapsulation. You already know what it is, because we already saw the video on it. So all this graphic says is, you know, hey, we start with the physical layer, our bits, and that's our data, and then we move up to the frame, and now our data goes here, and we add some other things that are layer 2 things. And then we go up to the packet level, and now this whole thing is in the data, and we add our IP information. Then we go up to the transport layer, and all this stuff ends up going here. So as we move up and down the chain, we are taking things off or putting things on, and that's what encapsulation is. So every layer wraps the data and goes through whatever protocol that it needs to go through to get that data where it's supposed to go. Or it strips the data off to get it wherever it's supposed to go, depending on which way you're going up or down the chain. So, for example, if we're starting at layer 7, we're in our web browser and we want to go get a web page like we did in our Wireshark labs. We're going to start with the data and the layer 7 header. As we go down, we're going to put our layer 6 stuff on, our 5, our 4, our 3, our 2, and then when we get to the very end, we have all ones and zeros. But all of this stuff is within this block. And that's what encapsulation is. Okay. Any questions before I